Okay, good morning, everyone. How did your homework go? Any questions? Okay. All right, so let's a little bit. Okay, the question started. So number 58. Which I was expecting. So we're gonna look at that and okay. All right, so one of a typical problem where we have a rational function. Degree of the numerator is larger than the degree of the denominator. So we cannot immediately start partial fraction decomposition because it fails. So we have to divide and then do partial fraction. So very typical scenario. So we're going to divide. And then let's see what we have. We have x to the power 4. We divided by x to the power 3, which is going to give me an x. Then x times x cubed, that's x4, plus 9x. x4 minus x4 cancel each other out. That's the idea. I will have minus 9x plus 1. The degree here is 1. The degree here is 3. We stop the division when the degree of the remainder is less than the degree of the divisor, of the denominator. So
I have a question.
I'm listening.
Wouldn't it be 9x squared?
Did I mess up?
I'm not sure, but you multiply them on top, right?
Yeah, I did mess up. Okay.
All right.
So we go over it again. The degree here is still less, so we're gonna stop right there. And this is my remainder in this case, and that's the quotient. So the goal of this is basically this long division tells me the following: that the expression x to the power 4 over x cubed plus 9x can be written much easier. It could be written as x plus minus 9x squared plus 1 over x cubed plus 9x. So this expression could be written much easier like that. Okay, and now we know that we need to integrate. Okay, so we know that we need to integrate. We know that. So this is simple. There is nothing into it. We need to work with this piece. We need to integrate that piece. All right. If we look at this piece again, that's again a rational function. The degree of the numerator is less. So what we've learned before, hold. So to integrate this, I need to, again, decompose it. So we're going to do the decomposition, and then we put the whole picture together. Equal. The first step in any decomposition is breaking up the denominator fully, factoring it out until I can't factor anymore. Total factoring out. And this is minus 9x squared plus 1. X squared plus 1 cannot be factored, so we always have to check that we can. So this can't be factored. Can't be factored. Since I cannot factor it, then this is going to give me, I'm going to break it into a over x plus bx plus c over x squared plus 9. And we're almost at the end of the problem. So now, as usual, so I'm working on this piece now. I have to multiply across by, so multiply across by x times x squared plus 9. And then this will give me the following: minus 9x squared plus 1 equal a plus x bx plus c. And now we have to find the coefficient ABC. In this particular problem, putting coefficient of x squared together, coefficient of x together, and c would be a little bit easier than plugging in value. But either will work. So we're going to use the second approach in this particular problem. Coefficient of x squared. So we have to basically do that. Distribute. And after we distribute, coefficient of x squared together. Everything in x together, constant term together. And this is minus 9x squared plus 1. So finally, this tells me that the coefficient of x squared here is a plus b. The coefficient of x squared here is minus 9. So we have a plus b equal minus 9. First relationship between the coefficient. Coefficient of x here is c. Here there is no coefficient. It means that the coefficient is 0. So this will give me that my c will have to be a 0. Finally, the constant term here is 9a. I want this to be equal to 1 and equal to 1. So it's fairly simple to find ABC. So we write down here, I get a equal 1 over 9 off the back, c equal to 0, c equal to 0, and the first one give me a equal, sorry, we need b. We have a already. b equal minus 9 minus a means minus 9 minus 1 over 9. Common denominator, 9 minus 81, minus 81 minus 88 divided by 9. All right. So my picture now is almost there. So now I go back to my original one, the one I'm interested in, which is that piece, and I put the whole thing together. Equal to x plus. Now we decompose that. When we decompose it, we get a over x. My a was 1 over 9, so I will pull immediately the 1 over 9 in front for x. So this a was 1 over 9. The c was a 0. And the b was minus 88 over 9.
Isn't it minus 82 over 9?
Is it minus 82? Yeah, why I do minus 88? Because I did this problem with one of your classmates yesterday, and I memorized the answer. Okay, yeah, minus 82. Thank you very much. And c is 0, and this is minus 82. So finally, I get. So now I am done. Plus, now the c is 0 is gone. So here I only have minus 82 times x in the numerator. So I can feel comfortable putting the minus 82 over 9 in front, x over x squared plus 9. The only reason I'm comfortable doing that because the c is equal to 0. Otherwise, I will not be able to do that. So now each term is easy to integrate. So the antiderivative of that equal to antiderivative of x, which is easy, plus 1 over 9 is a constant. I can pull it out. Antiderivative of 1 over x minus 82 over 9 is a constant. I can pull it out. And I will be left with the antiderivative of x over x squared plus 9. Okay. Every piece by itself. So it's a half x squared plus ln of the absolute value of x minus 82 over 9 times. Antiderivative of this, that's the typical u substitution because the derivative of x squared plus 9 is right here. So right there, I need to do substitution. U equal x squared plus 9. Du will give me the dx. And I will end up with a half ln of x squared plus 9 plus and of the proof. Okay, questions before I look at the other two? I probably will pick one of them, but I'll give a hint for one and do another one. Let me see them. Okay, question before we proceed. All right, so let's look at 67 and 77. So 77. Ex over ex minus 1. So I said I may not finish the problem because I think equal. All right, so quickly, how would you do this problem?
Substitution.
Substitution, immediately. Substitution is screaming. What is the substitution?
E to the x.
Right, immediately u equal e to the x. Because we can see that I have ex minus 1 ex plus 2, and the derivative of ex is really looking at us. The du is the ex dx. And then this would become integral of u minus 1. So they even factored out the denominator for us. So they left nothing for us to do du. And now the rest is straightforward by now. That is, we have to factor out partial fraction decomposition. So that's the easiest possible scenario at this stage. So this would give me 1 equal okay, and then I pick my values, u equal to 1. Picking values here, I think, is the easiest way to go. It would give me 3a. This would give me a equal 1/3. Done with that. Then u equal minus 2 will give me 1 equal, this is gone, minus 3b. b equal minus 1/3. Done. All right, so this tells me that the integral, so this integral is equal to the integral of a, which is 1/3 times 1/u minus 1, plus b is 1/3, 1/u plus 2, du. So finally, I will get 1/3 ln of u minus 1 minus 1/3 ln of u plus 2 plus c. Last step is go back to the original variable. So this is a very simple substitution, which will actually get us through the problem. So finally, we have to look at number 67. And as I said, I will probably set it up without having to solve the whole thing. Any questions before we move on to the last problem? So 67 always bringing us back up to the idea of the area of the region. So we should never forget that. So the question is, find the area of the region which is bounded by the following curve, y equal 10 over x squared minus 2x minus 24 for x between minus 2. So it's bounded by this curve, the lines x minus 2x and the x-axis. Okay. And as it is for area, as I said before, I'll say now, without graphing, I really don't know what I am dealing with. I cannot just jump and say it's the integral, because this could be negative sometimes, positive sometimes. So I do not really start doing this unless I actually graph the function. And you can either, if you know the graph, you're fine. I think if few of us do know it. So the easiest way is basically to go use your calculator or use decimals is the one I use. So I'm going to use decimals and try to graph it because we have to. So we use decimals here. You guys can use it while I'm doing it myself as well. And probably I should share the screen with you. So I'll share the screen and graph the function. Okay. So I will have 10. I mean, the 10 does not really matter. It's not important. Divided by x to the power 2 minus 2x minus 24. So that's the graph. Okay. And they wanted between, I think this book, like, have I done this problem before? Looks very familiar. And it's between -2 and 2. So that's how the graph looks like. That's -2 and that's 2. And the graph look like that. This is -2 and this is 2. Okay, so without the graph, I really would not even start graph. So now I stop the sharing part and now I go back. So that's -2. So that's really the area I'm interested in. Okay, so we'll do the setup. Okay, what's the setup? What's the area? Okay. Again, as usual, we have to take a slice and we have to compute the area of the slice. But here, if we are careful, the upper area is the line y equal to 0, so we have to be very careful here. And the bottom one is the 10 over x squared minus 2x minus 4. So the integral here is going to be the integral from -2 to 2, not of y, of, if you want, 0 minus that. So we have to be very careful with this. And if my memory is correct, which is it is, I'm sure I did this problem before. So now that's minus the integral from 2 of that. Okay, so it's minus because here the graph lies below the x-axis. So my function is not positive. So I cannot put the integral from -2 to 2 is actually minus the integral. Or you can say it's the length from here to here, which is the height of a typical triangle, is minus that. It's not the plus. And the rest, I think, is fairly easy at this stage. I will not complete it because the rest is you just factor out the denominator. I think this denominator can be factored. And then you proceed with partial fraction decomposition. All right? Okay. Any other questions before we proceed to the last integration technique of this course? Anybody else? Okay. Let me ask you a simple question. Suppose I give you the following expression and tell me if it's true or false. So I'd ask you to decompose the following if possible. Or write the decomposition. You know, don't decompose, just write the decomposition. So a student write the following. So the true or false?
It's false.
Because?
Because you have to use long division because P of X is equal to Q of X, the degrees.
Absolutely correct. This is false. Okay, so you don't immediately factor. You have to make sure the degree of the numerator is less than the degree of the denominator. So this is absolutely false. Okay, because here the degree of the numerator, because the degree of the numerator is equal in this case to the degree of the denominator. So you start the partial fraction decomposition, you have to make sure the degrees work. Otherwise it fails. So in this case, you have to go after, first we have to divide, and after you divide, and then you can factor. So this problem, so now to divide, you have to rewrite it as x squared minus 4. And then if you want to decompose this, then you have to start the division process. You have to do that. Means you have to take x squared plus 1 divided by x squared minus 4. And then that's going to give me easily the 1.
Would it be x squared minus 16?
Yes, of course. I always do stupid mistake, don't I? Thank you very much. Okay. Very good. So this will give me 1 minus minus. It's give me a 17. So if you want to decompose this is going to be equal. 1 plus 17 over x squared minus 16. Now things make sense. After we do that, this piece is the safe piece to decompose into x minus 4 and x plus 4. Okay, so we have to be careful. Don't just jump to decomposition. The decomposition work when the degree of the numerator is strictly less. So if it's bigger or equal, there is no way out. We have to divide because mathematically this is false. This cannot hold. There is no way you can make this equality hold. And this is because what we mentioned yesterday, due to the degree. So if I do what I did before, I will have degree 2 equal a degree 1, which doesn't work mathematically. Okay. All right, so now our problem for partial, whenever we have a rational function, any rational function, we actually know how to do it. We first factor out denominator completely, and we look at the degree. If the degree of the numerator is strictly bigger or equal, long division will bring me to the scenario of the degree of the top less than the degree of the bottom. Once I hit this scenario, total factorization of the denominator, then we do the decomposition based on the type of factor we have. Linear repeating, quadratic, that we cannot factor. Right? Okay, so the last piece we will be doing, and we basically wrap up our integration technique, is the following type of integral. So now I'm moving back to section 8.4 because 8.5 is actually more important in terms of integration. So the integration for me, the most important integration technique is substitution, followed by integration by parts, then partial fraction decomposition, and then trigonometric substitution that we will be doing now. But the substitution by parts are basically the most important integration techniques. So we move back to section 8.4 in your book. So 8.4, trigonometric substitution. Okay, first let us see what type of integral we will be working with. So as usual, I'm going to put 2 integral in front of you, and I'm going to ask you which is easy and which is hard. So suppose I put this one. Versus this one. Okay, 1 and 2. Which one is easy? Which one is hard?
2 is easy.
Which one?
2?
2? How would you do it?
Isn't that arc sine?
No, arc sine is 1 minus. No,
I would say the first one is easier.
Yeah, arc sine is, I'm glad you remembered that. Usually I even forget the arc sine, it's minus.
Minus, okay.
It's minus, crucial, it's minus. Okay, so, nope. Somebody else said something. What else?
I would say the first one is easier
Because?
because then I just use substitution.
Exactly, the first one is fairly easy. The first one, we just put u equal 1 plus x squared. The du is the 2x dx. I am basically done. So this will give me a half integral of 1 over the square root of u du. okay, which will give me a half the integral of u to the minus a half du, which is a half 1 over minus a half plus 1, which is going to give me 2 u to the power minus a half plus 1. So which will give me the square root of u plus c, which will give me the square root of 1 plus x squared plus c. Okay, so this one is actually easy because I can put u to be 1 plus x squared. This one is the hard one because your classmate said arc sine. I'm glad he remembered the arc sine, but the arc sine, it's a minus. It's not a plus. It's a minus, and that's important. So the question is how to integrate that. It's this type of integral that we're interested in. So the type of integral in general that we're interested in this section. So we are concerned. So we are interested, basically, to the goal of this section, if you want. We are interested in evaluating, in this section, integrals that involve the following expression. Integrals that involve the following expression. Square root expression. So we are interested in evaluating integral that involve the following expression. Expression like 1 plus x squared, but we will do it in its more general case, a squared plus x squared, where a is going to be the constant, or a squared minus x squared, a is a constant as well, or x squared minus a squared, a is a constant. Okay, so this is the type of integral we are interested in. Okay, so before we do that, there is one integral I like to establish because we will be using it tremendously in this section, and then we start talking about how to handle those type of integrals. So I will establish the following. In this section, we will be integrating function that involves sine and cosine. Eventually, you will see how this will come up in a minute. So I need to establish the antiderivative of all the trig functions. We know the sine. We know that that's minus cosine theta. We know the cosine. It's sine theta. Okay. I did in class the tangent theta. And I will give you the answer, but I would like to remind you how we did it. We said that's the sine over the cosine. And if we do a very simple substitution, which is u equal cosine theta, this would give me minus ln of cosine theta. Okay, so these are the ones that I did in class. Now we still have one, is the integral of secant theta. What's the antiderivative of secant? Okay, I'll show you how to get it, but usually you either memorize it or you use it whenever it comes up. So the one I'm going to establish is antiderivative of secant. So what's the antiderivative of secant? All right, it's going to be ln of secant plus tangent theta plus c. Okay. That's going to be the antiderivative. So let me show you a little bit where this formula comes from. It's a trick because there are some very smart people out there who comes up with very nice tricks. So let's see how it works. That's the trick. I'm going to take secant theta. So I'm going to say y. And I'm going to multiply it by that and divide it. I can do this, but that's the trick that's involved in evaluating this integral. And then we're going to do the following substitution. I'm going to set u to be secant plus tangent. All right. If I do that, what's the du? Okay. Okay, what's the du? What's the derivative of secant? Secant, tangent. The derivative of tangent, sorry, du equal secant tangent plus the derivative of tangent is secant square d theta. All right, does this substitution help? I know it's a trick. I'm not expecting you to think about it. I probably didn't think about it, but somebody is bright enough to think about it. Why do you think the substitution will do the job? Anybody can see.
We have that in our numerator.
What?
Our numerator has the derivative.
Right, if you look at the numerator here, the numerator is actually the du itself. Let's see why. Because here, if I factor out the secant, I will be left with tangent plus secant d theta. So the numerator is du. And then I will have 1 over u du. So it's a very ingenious way of finding this integral. Very, very ingenious way of finding the integral. So this would give me with ln of u plus c. It means ln of secant plus tangent plus c, and of the why this work. Okay, very, very clever way of doing it. Okay. So now we established those integral. Now we go back to our main goal in this section, which
I have a
is
question.
yes.
Real quick, can you go back to the tangent one at the end? It was like
Oh yeah.
negative
Yes. How do I do it? Remember.
Oh.
I put u to be the cosine. Okay? The du would be the sine of theta. So this would have become integral of, the du is the minus. This would become sine theta d theta. This would become minus 1 over u du minus ln of u. It means minus ln of cosine theta plus c. Okay, the student will ask this question. Does that make sense?
All right. Yes. Thank you.
So that's how we should do it. Okay, so now we're going to go back to how to find our antiderivative. I'm going to put, before I even start the rule, our guidelines, I mean, the 3 identities that we're going to use tremendously in the sections are. And remember, we've talked about that, the relationship between sine, cosine, and we've talked about the relationship between secant and tangent. So by using the main trigonometric identity, cosine square plus sine square equal to 1. So we have the following, which one I use? Cosine square theta is always equal to 1 minus sine square theta. And this is derived from cosine square plus sine square equal to 1 will give me that, okay? And then there is another identity, which is secant square theta is 1 plus tangent, and you will see in a second why I'm gonna need those. And then tangent square theta is secant square theta minus 1, okay? And every time I'm gonna bring back those identities, so because that will be the guideline about what you're gonna be doing. We're starting now. Okay. So I'm gonna go back. I'm gonna evaluate. The question is evaluate the following integral. I did all the prep needed. Integral of 1 over the square root of 1 plus x squared dx. Okay. What's really make it very bad, very hard to deal with, first substitution failed, and the square root term is problematic. So the idea is we're going to make a substitution, which somehow help me to get rid of the radical term or of the square root term. So we're going to do the following substitution, slightly different than the regular substitution in the following sense. I'm going to set x to be, x is the variable, it's my old variable. I'm going to set it to be tangent theta. So theta will be my new variable, and I'm going to set x to be tangent theta. Okay. And we'll see what's the benefit of that. So usually I put u as a function of x. Usually in the regular substitution, u, which will be the new variable, is given as a function of x, like 1 plus x squared, for example. In this substitution, x is given in terms of your new variable. So x is tangent theta. The rest will be verbatim how we did substitution. But it's this one that's going to be a bit mystery for you. Where is it coming from and how you're going to choose it. All right. The rest is going to be verbatim what we do. Once we find x, we find dx. What's dx? So basically, we find dx. So here, x is a function of theta. So I need to find dx d theta, which is secant squared theta. It means dx is secant squared theta d theta. So now the regular substitution. And now I'm going to substitute everything verbatim in terms of theta. Okay, the dx, this will become secant squared theta d theta. Okay, and 1 plus x squared will become 1 plus x squared. X is tangent square theta. Okay, all right, is equal to. And now we will see the benefit of the substitution. The benefit of the substitution. Secant square theta 1 plus tangent square is equal to what? Secant square. So 1 plus tangent square is secant square. So by plugging in tangent theta for x, this became secant square theta times secant square theta d theta. So what is the benefit of plugging in the square root? What is the benefit of plugging in x equal tangent? Can anybody start seeing the benefit? What did it help me to do?
Will you be able to cancel out the secant squares, thetas on each side?
Exactly. And that's the benefit of my substitution. So this is going to become 1 over secant theta. So somehow I got rid of the radical term, of the square root term. So the goal of this substitution, that's very bizarre at the beginning, is basically to create a scenario. So instead of having x squared, I said if I had tangent squared here, 1 plus tangent squared give me secant square. And I can basically get rid of the square root. The rest is going to become a trigonometric integral in secant and only secant in this case, okay? Which is going to be equal to secant over that, secant theta d theta. Which is, as I started the lecture with it, I mean not started, but I established this because we're going to use it a lot in this section. Very good. So that's the LM. Am I done? Am I done?
No,
No, because
the square root sign.
yeah.
Maybe. I'm not sure. Okay.
Am I done?
You got to replace x back in for
Exactly. I have to go back to x. because now my integral is a function of theta. I have to go back to x. So I'm going to go that here. Or I put it in red just to emphasize it. I have to go back to my original variable. Go back to x. Means I need to substitute everything back in terms of x. All right, to do that, I have to remember what's the relationship that existed initially between x and theta. So I have to go back to x. So what's the initial relationship? Initially, x is tangent theta. That's the initial relationship. So when I'm substituting here, the tangent is not problematic. This is x. But the question is, what is secant? So if I know tangent, the question is, what's the secant of theta? Now we can go two routes. I will explain one route because it's easier. So what's the secant theta? The way we're going to find it is the following. We're going to build a little triangle. A triangle. And I'm going to label the triangle. I'm going to pick an angle. It doesn't matter which one except the right one to be theta. Okay. And then I'm going to label the triangle. So the tangent of theta will be x. So what do I mean by that? The tangent is what? The tangent is opposite over hypotenuse. So I'm going to label it so that the tangent of theta is x. So I'm going to put the opposite to be x, the hypotenuse to be 1. By doing this, the
Professor, is
tangent,
the tangent opposite over adjacent?
yes, of course. I'm going to label it so that this is x and this is 1. Okay, but now I need secant. What is secant? Secant is 1 over cosine, right? So to be able to find the secant, I need the cosine. But now can I find the cosine in this picture? What's the cosine? The cosine is adjacent over the hypotenuse. But can I find the hypotenuse in my scenario? Is it easy? I'm going to use Pythagorean theorem. So Pythagorean theorem tells me that the hypotenuse, so let me call this is C, told me that C squared is 1 plus x squared. So the C is the square root of 1 plus x squared. So there are a lot of steps in this problem, but once we get the hang of it, it will not be hard anymore. So the cosine is that, so the secant is 1 over cosine. So if I divide 1 over cosine, is going to be the square root of 1 plus x squared. So my secant now is the square root of 1 plus x squared and of the problem. Okay, so there are a lot of steps involved in those particular trigonometric substitution. Step number 1, we're going to pick the right substitution. So today I only do that. Tomorrow we will do more. So here we picked x equal tangent because it's going to make this x squared tangent square, making the problem, helping me to get rid of the square root. Once I did that, I got an integral in secant. We know the antiderivative. So, but this will give me only an integral in theta. And now the question is how to go back to x. And then we say, okay, what's the relationship between theta and x? X is the tangent of theta. So I constructed a triangle and I labeled it so that it reflects this picture. So tangent is opposite over adjacent. So I labeled the opposite x, the adjacent one. I picked the labeling the way you want, as long as it will match the picture you have. And then I wanted the cosine. The cosine is adjacent over hypotenuse. Pythagorean theorem gives me the hypotenuse. And then the secant is 1 over cosine, which will give me that. Now I expressed everything in terms of x and of the problem.
I have a question.
Yes.
What thinking did you use to first change x to Yeah,
Tangent?
tangent x.
Yes, the thinking
Yeah.
is going to be totally hidden in those identities. Okay, totally hidden. So I have 1 plus x squared, all right? And I want to make the substitution. So we had, that's the idea. We have a square root of 1 plus x squared. And I said, I want to make a substitution so that this term here, after the substitution, will be something squared. So I can get rid of the radical. So I said, okay, which one will give me? If I put x to be tangent, I'll have 1 plus tangent squared, will giving me secant squared. I can't get rid of the radical. Did you follow a word I said?
Yeah, okay. So what you mean is
What
you
I
choose
mean is, yes, what I mean is something. If I had 1 minus x squared, okay, we're gonna do all those, but now because you asked the question, let me push you. If I have square root of 1 minus x squared, what substitution do you think we will do? If my integral,
wouldn't it be sine
it's
squared,
gonna
right?
be not sine squared, it will be sine.
Oh, just sine. Sorry.
X will be sine theta. Then the 1 minus sine squared will be the cosine squared theta. I got rid of my radical. That's the thinking into it. If my integral involves x squared minus 1, okay? And then what substitution is going to work? X equals secant theta. These are the guidelines. That's why I'm not gonna make you memorize anything. That's the only thing I want you really to learn. Once you know that, and then you know which substitution work with every situation. That's why I said these are going to be our guideline. Okay? All right. Problem number 2 I'm going to do, I'm still sticking in with this scenario, but I'm going to make a slight change, and you will have to tell me how my substitution is going to be affected. So you guys should have this in front of you. I have to remove it. I'm going to take the second example, which is exactly verbatim the same, but I want to make a slight change. So example number 2 is evaluate the integral of 1 over the square root of 4 plus x squared dx. Do you see the change I did? Okay. Now, what's the substitution that will save me in this problem? What shall I do? So what shall I do for substitution? Okay, if I put x equal tangent theta, let us say I do that. Will this work? What do you think? My goal is really to create a scenario so that I have a complete square down here. So if I put x to be tangent, do you think the problem would be solved? So you don't have to write, we're just thinking. This would give me that. It means 4 plus tangent square theta. If I do this, will this get me anywhere?
I don't think so, no.
So how can what game can I play so that I can get somewhere?
Could you take out a 1 over 4 from the whole problem?
I can do that. Yes, that would work. But we can do it in a slightly different way. That would work. That would work. But then you need another substitution. Okay. All right. The game we're going to play, watch carefully what it is. I don't want this 4 because it's problematic. It's really problematic. I want a way to have 1 plus tangent square. So the game we're going to play is, I will put here 2 times tangent. One of your classmates suggested that on chat. What's the benefit of this? What's the benefit? X squared will become 2 tangent times 2 tangent, 4. Can you see where this is heading? Does anybody see where this is heading?
Yeah, you're just going to factor out the 4, so that leaves you with 1 plus.
Right, I'm gonna factor out the 4. This would leave me with 1 plus tangent square. So we're trying to explain where we come up with this 2 from. It means this is will give me 4 secant square. And then we are good. Okay, so when I have a 4 here, what I'm going to do is take the 2 tangent so I can basically get rid of the square. So now I will do this problem quickly. It's going to be a verbatim repetition of what I did a minute ago, but now I will clarify it. So that's the goal. That's the justification of my choice. And now we proceed. So x is this. So dx is going to be 2 secant squared theta d theta. And this would become integral of 1 over the square root of 4 plus 4 tangent squared theta. Dx is 2 secant squared theta d theta. Verbatim, verbatim. It's equal to, remember that, you cannot make the substitution correct enough to be able to do this. So times 2 secant squared theta d theta. So now the rest will be much simpler. That's going to be 1 over the square root of 4 secant squared theta, which would be equal to integral of 1 over, my whole game is to create a scenario where there is no radical term. So that will be 2 times secant theta, 2 secant squared theta d theta. So I did the same problem. So the only reason here is say, what if I had 4 plus, what to do? And now my 2's cancel out, secant square over secant, which will give me a secant theta. Secant theta is the ln of secant plus tangent plus the c. And now my last step in the game is back to x. Back to x, I have to back up. The only way to go back to x is say, what's the relationship that existed initially between x and theta? So, because I need to go back to x. So what the relationship between them? So x is 2 tangent theta. I need tangent and I need secant. So if x is 2 tangent theta, it means tangent theta is x over 2. And now, let's see what we have. Tangent, I am safe. Tangent is x over 2. I have secant to really deal with. Now, how can I find the secant? Verbatim, what I did, I'm going to build a triangle and label it. Pick any angle to be theta. Label so that the tangent will be x over 2. For b to be x over 2, it means I label this as x. I label this as 2. Exactly. And then this would be by Pythagorean 4 plus x squared. And now I need the secant. The secant is 1 over the cosine. But the cosine is 2 over the square root of that. So the secant could be 1 over this, means it will be the square root divided by 2. And end of the problem. Okay. All right, so your homework is on Brightspace, on MATLAB. Good luck with it. End of the section.